So now that your memory has been refreshed on what a group is and what are some of the examples of groups that we're going to care about this semester, it's time to take the next step and look at the basics of group theory, part 2. What we want to do is look first at how to make connections within groups. In other words, how to find smaller groups within larger groups. Naturally, those are called subgroups. And then we'll also look at homomorphisms, which are the functions from one group to another group that will allow us to compare how one group operates with how that other group operates. So in the basics of group theory 2, we're going to talk about three things. Subgroups. What are subgroups and how do they work? Cosets, which are a topic related to subgroups or just shifted subgroups. And then homomorphisms. What are they? How do they operate? And what can we do with homomorphisms? So let's get started. First of all, what is a subgroup? Naturally, a subgroup is just a smaller group within a larger group. In other words, we have some subset of the elements of the group G, and the same operation that makes G a group also makes H a group. So keep in mind that that operation which goes on the subgroup H is the same as the operation which belongs to the larger group G. And the same thing is true of all of the other attributes. The closure, the identity, and the inverse properties that define a group also have to hold inside of the subgroup H as well. So it's just a small group living within a larger group. So for example, if we take a look at the group of integers, the natural numbers, the set of natural numbers 1, 2, 3, 4, 5, and so forth, do satisfy the closure property, because if I take and I add one natural number and another natural number, the result is going to be another natural number. 2 plus 3 is equal to 5, for instance. But unfortunately, the natural numbers don't satisfy the other properties that might have otherwise made it into a subgroup of the integers. It doesn't satisfy the identity property because the identity of the additive group of integers is 0, and 0 isn't a natural number. Also, it doesn't satisfy the inverse property because the additive inverse of a natural number is not a natural number. So even though 0 and the negative natural numbers are still members of the group Z, the larger group, since they don't belong to the subset n, that doesn't make n into a subgroup. So the natural numbers are not a subgroup of the integers because we need closure, identity, and inverses all to belong to that subgroup. Let's look at an example taken from finite group theory. When H is a subgroup of G, by the way, we'll write H as less than. We use the less than symbol to denote subgroup. Some authors will just use the subset. Some authors will write less than or equal to. There's a variety of different ways of denoting it. We're going to stick with the less than symbol to denote that H is more than just a subset of G. It also is a group, a subgroup, using the same operation that G has. So here's an example. Let's take the familiar clock face group, which is just the additive group of integers modulo 12. So arrange the numbers around a clock face. Let's think about what a subgroup might look like. Well, first of all, every subgroup has to have an identity element in the group, and that has to be the same as the identity element of the original group. So whatever subgroup we have has to have the identity, which in this case is 0. If that's all it has, then we're going to call that the trivial subgroup. So the subgroup consisting of just the identity element is indeed a subgroup. But suppose I want to have something else. Suppose I also want 2 to be a part of this particular subgroup. Well, because we need closure, we also need 2 added to itself to be a member of this group. And 2 added to itself with this operation is naturally 4. But then again, because of closure, we also need 4 plus 2 to be a member of this subgroup, 4 plus 2 being 6. Then we would also need 6 plus 2 to belong to this subgroup, so we need 8. We need 8 plus 2, so that forces 10. And we need 10 plus 2, but what is 10 plus 2 modulo 12 but 0? So in fact, 0, 2, 4, 6, 8, and 10 taken together now satisfy closure. We can also verify that it satisfies the inverse property, that namely every one of these elements, 0, 2, 4, 6, 8, 10, its additive inverse also belongs to this subset. For instance, the additive inverse of 4 is 8, and both of those belong to this subset. So that does in fact make this collection into a subgroup. In fact, it's something a little more. It's something that we call a cyclic subgroup, because how did we get this subgroup? We just took a single element from our group, and we just looked at all of its powers. And here powers just mean we operate on the same element with itself a number of times. So in the case of the additive group, we were adding the number 2 to itself repeatedly. So the cyclic subgroup generated by an element consists of all of that element's powers, both positive powers and negative powers. So this is the set of all powers of an element G. So in our previous example, we were looking at the subgroup we called H2. We would call it the cyclic subgroup generated by 2. So it consists of 2, 2 to the power 2, which again, because power here means in the additive group is adding it to itself. That gives us 4. 2 added to itself 3 times, 2 added to itself 4 times, 5 times. Then when we added 2 to itself 6 times, we got 0. So that we would say that the so-called element order of the number 2 in the additive group of integers modulo 12 is equal to 6. It's both the smallest power for which the element raised to that power gives us the identity. It's also the number of elements that are in the cyclic subgroup. Those are two different ways of proving that. Here's a quick little proof that the cyclic subgroup generated by an element of a group indeed does satisfy the properties of the subgroup. So let's look at closure, identity, and inverses. First of all, why is the cyclic subgroup closed under the operation of the group? Suppose I take two elements with powers k1 and k2. If I multiply them together, what do I get? Well, just by the properties of exponents and powers, which work in a group just like they work anywhere else, what we get is the k1 plus k2th power of g. And because k1 plus k2 is still an integer, and the cyclic subgroup consists of all integer powers of g, that means that this element also belongs to the cyclic subgroup generated by g. So closure is verified. How about identities? How do we know that the identity of the group belongs to the cyclic subgroup? Well, the identity is just the 0th power of the element g, and because 0 is an integer, that implies that our identity belongs to the cyclic subgroup as well. And finally, what about inverses? Suppose I have an element g to the k. What is the inverse of g to the k going to be? Well, it's nothing other than g to the power minus k, and because for any integer k, minus k is also an integer, that implies g to the minus k belongs to this cyclic subgroup as well. So indeed, the cyclic subgroup generated by an element, in other words, the set of all powers of that element, does in fact form a subgroup of G. Let's take a look at another more interesting example drawn from a group that's not abelian. Again, this is the symmetric group on 4 symbols. And because symmetric groups are so interesting, it turns out there's going to be a lot of different subgroups that we could choose from. So let's just pick a single example of an element in S4, say 1, 2, 3, the 3 cycle that turns ABCD into CABD, and let's look at the cyclic subgroup generated by that element. So naturally, it consists of the element itself, the first power, then the second power of that element. So we'll look at 1, 2, 3 composed with itself. You can see from this little anagram here that what we get is 1, 3, 2 when we turn ABCD into BCAD. Then we need the third power of 1, 2, 3, which, composing again, we find out that that third power actually is just the identity, because after we've applied 1, 2, 3 3 times, we get the identity. We get ABCD back. Now let's look at another example where we look at a cyclic subgroup generated not just by one element, but by two different elements of S4, 1, 2, and 3, 4, the two adjacent transpositions. So what is this going to have in it? Well, it's going to have 1, 2 for sure, which turns ABCD into BACD. It's also going to have 1, 2 squared, but naturally 1, 2 squared, if we swap A and B and then we swap them again, we end up in the same place we started. So 1, 2 squared is the identity. It's going to have 3, 4 in it, which transposes the third and the fourth symbols. It's also going to have the second power of 3, 4, which again is the identity because we've just swapped the third and fourth elements twice. But then because this is a subgroup, we also need it to be closed under multiplication. So we need 1, 2 composed with 3, 4 to belong to this subgroup as well. That turns ABCD into BACD. But then because of closure, we also need that element composed by 1, 2 on the left to belong to the group. But if we compose it by 1, 2 on the left, we get just plain 3, 4. We also need that element composed by 3, 4 on the right to belong to the group. But naturally, that's also equal to 1, 2 because 3, 4 composed with itself is the identity. What if we compose by 1, 2 on the right? Well, we find out that what we get at the end of that is just 3, 4 again. And then if we compose by 3, 4 on the left, we find out 3, 4, 1, 2, 3, 4 gives us just 1, 2. So in fact, the set of all products and powers of 1, 2, and 3, 4 is this subgroup that just has 4 elements. And just to finish this up, verifying that 1, 2, 3, 4, when we square it, well, when I square this element, I just found out a moment ago that 3, 4, 1, 2, 3, 4 just gave me 1, 2. And so this square also reduces to the identity. So here's an example of a cyclic subgroup, a couple of different cyclic subgroups of the symmetric group on 4 symbols. One of them had 3 elements in it, the other one ended up having 4 elements in it.